All right, there's a few people coming in. I'll wait until it looks like we have a few more people. The club meeting's just wrapped up on the repeater. Looks like we're up to 12 people in the chat. And as we go through this, I'll have a couple spots I will try to wait for any questions. The live chat should let people type in if you have a question about it that I can try to answer. I'll be trying to keep an eye on that as we go. Wait another minute or two in case anyone else is still trying to get in. And keep the radio low enough it doesn't bleed over. Hopefully everyone can hear me clearly enough through this. Very good. I see a couple of comments coming in that people can in fact hear me, so that's excellent. Try and get a copy of the stream up myself so that I can see what everyone else is seeing. All right. Looks like it's been at 13 people for a bit, so I'll go ahead and start. So I'd like to talk to you tonight about the solar power digital station that I was running on 2019 Field Day. I know a number of people were able to get in and look at the setup I had. I got to talk to some people, but I didn't get to speak in depth as much as I would have liked to. So I'm trying to fill in some of that information with this presentation. So let me move forward. So this is what the outside of the tent and setup looked like. So it seemed like it was a reasonably good area. I got up there on top of the tent. I had the foil to keep us a little cooler, and then over on the side here you can see we had batteries up against the tree. So let me move forward on to some interesting. So initially I want to give a brief overview of how the block diagram was for the data and radio portion of this, so you have a little bit of an understanding of what all equipment was connected. And much of it required power in various ways, since obviously you have to run a computer to do data, and I'll get more into that in a moment. So obviously you need your power, 13.8 volts, and then have to have a radio. That's sort of a given. So here you can see I had the power came in, went to the radio, had the head unit, an auto tuner, some coax filter stubs on out to the antenna. Well, we're going to need to have a computer for logging and radio control, rig control, and then need to have something to power that computer. So had a car charger that outputted USB-C power delivery, which the laptop is capable of using, and a docking station so that we could connect multiple things to the laptop, because there were a number of things we needed to connect into this, and my laptop only has a couple of ports. So first things first, have to have that USB connection to the radio. On my radio, the ICOM 7100, that gives me both the audio sound card for interfacing as well as a serial port for rig control. And need a cellular modem. I was running FT8 for a fair bit of it, and that requires a good time sync. The cellular modem gave me an internet time source, so I could make sure my computer clock stayed accurate and keep a good lock on the time slots for the signals. as I was transmitting and receiving. Since I had that, I might as well have a Wi-Fi access point. I had a tablet, so when I went over to eat, I could still keep an eye on things, run things remotely. Or if someone else needed to download something, I was running a Wi-Fi sharing so that there was internet sharing if someone else needed to browse the web or wanted to look up a call sign or whatever. Here's a picture of the inside of the tent. So you can see I had the laptop on the table, ICOM control head. The main unit was an ammo can along with the auto tuner down underneath the table. And then the coax stubs rolled up there on the floor next to me before stuff ran out the side of the tent. And here's a little better view of the top of the table. So I had the computer here, and then over here you can see I had the laptop dock I talked about, the cellular modem. The power sockets are just a box I made. It's a Radio Shack project box. It's got 3 automotive style connections, so that lets me easily plug in things like the car charger for the Yaesu radio, a car charger to run the laptop dock, and then I had a USB power supply for the Wi-Fi adapter to provide its power, a little boost converter. So yeah, that's moving on into the topic of the power. So from the batteries, I had 3 Walmart flooded lead acid batteries. Each one was 12 volt, 100 amp hour at a 20-hour discharge rate. It seemed like that gave me a good amount of power. I had to get new ones because the ones I used in 2018, I think it was, seemed like they were running down. They weren't wanting to hold the charge as good. In 2018, I think it was, where I had partway through the night, it seemed like the voltage was sagging down especially bad. Also, for the people who just joined, I see it's up to 20, some more people had joined. If you have questions, feel free to put them in the live chat. I'm trying to keep an eye on that as I go through this. So I have a few spots I'll try and stop and wait, but I will try and keep an eye on the live chat in case people want to type in any questions about this as I go. Yeah, the batteries, pretty much just put them all in parallel. Each one has a fuse, so that way if something goes wrong, say one of the cells goes short circuit, it'll blow the fuse. It's not going to cause the battery to blow up or start a fire or something. I didn't bring it. I meant to as a prop, but so over here where I have the diagram of the three lines here, actually what I built was a sort of a squid-shaped thing that had 4 cables, 4 8-gauge cables coming out with quick connects. I use these Anderson SB quick connects. They're a pretty big beefy connection, and I had 4 of those so I can have up to 4 batteries or whatever. And it went into a automotive distribution block, and then out the other side I had, I think it was either 4 or 6 gauge, I don't remember off the top of my head, with another connection to link them all together and to try and also keep the length of all of the wires equal so that no battery would have a lower resistance wiring connection than any other. So that way they equally charge and discharge. So here's the picture of the batteries, a little closer up by that tree. You can sort of see here in the picture on the ground the distribution blocks, and there's an extra pigtail laying on the ground, and the 3 that are hooked up. And then over here where it's connecting into the cord going off the bottom is actually a set of jumper cables, heavy jumper cables that were cut up and had connectors put on. So that's a good heavy, I think that's a 6-gauge cable, about 10, 12 feet, runs into the tent, so that way I don't have too much voltage drop on my connections. So the solar panels. Got a new charge controller for my solar panels. These are all Renogy brand solar panels and a Renogy charge controller. I had 2 basic 100-watt rigid panels, and then I had one which was a fold-up panel. And the charge controller I got for this past year was a MPPT. I think it's maximum power point tracking. Rather than having to have all of the solar panels in parallel and then feed them out with really heavy cables to the charge controller, this allows them to be in series, up to 100 volts in series. And then it handles internally a buck boost converter, so it can try and figure out the optimal conversion to get the maximum wattage out of the solar panels. Also, that means I can run the same, I think it's 12 gauge wire that I had when I only had 100 to 150 watts of solar panels. I could use those same wires to run 300 watts because it was actually a lower current than when I had the 50 watt and 100 watt panels in previous years, but it was at a higher voltage. So that gave me a little bit less loss over the length of it. The other cool thing that this charge controller has is it has a Bluetooth module that can plug in. So it can give you all sorts of really handy statistics and data about what it's doing inside. And that's very helpful so that you can know how much power is coming in. I used it so I could try and tweak the angle of the solar panels and get the maximum amount of sun on them. So here's a screenshot of the software runs on a phone or tablet, and you can see where I had the solar input is, this was during a sunny part of the day. What time did that say? That was 10:09 a.m. So that would have been the following morning when my batteries have run down some overnight. And it was putting out 252 watts of power out of the panels. That came to 44.5 volts at 5.6 amps coming into the charge controller from those series connected panels. And then you can see at the bottom, the battery output was 13.2 volts at 18.31 amps. So almost 20 amps of power coming out of the charge controller after it does its conversions, but we only had 5.6 amps on the wires coming in. So that, if I had a simpler charge controller, I'd have needed wires heavy enough to handle the 18 amps or near that without too much loss. I probably would have had a fair bit of loss in the wires coming in. So I feel like that gave me a much better charge going on, and also it allowed me to have a longer run with thinner wires and not lose the power as much. So here's a picture of what they looked like. I just had them propped up next to each other, got a little bit of reflective tape on the corners so people don't fall over them in the evening hours. Here's the block diagram for the power. So this is where it gets a little bit more complicated because it sounds nice, oh, everything's 13.8 volts. However, it's a battery, so it's not exactly 13.8 volts, especially during the night when the batteries are running down. But I came up with a solution for that, and it seemed to work quite well. First, you have your batteries and your charge controllers, and you have the output. Now, I also wanted to be able to review how the charge and discharge was going. So to do that, I had a current shunt and a logging multimeter. That allowed me to see how much power, amps and volts, going in and out of the batteries. So I actually have, I did remember to bring this as a prop. This is called a Musha meter. It's not focusing on there. It's a little multimeter that has two channels. It has a low voltage that goes up to about 2 volts and a higher voltage channel, as well as a few other things. And that's connected to this current shunt with the big heavy connectors. And this is a 75 amp shunt. I'll talk a little bit more about the details of the wiring of this, but this thing can record every 1 second to a micro SD card by itself. And that allows me to have some pretty good data that I could look over. And I'm going to talk about that data later in this presentation. Oh, whoops, wrong keyboard. All right, so got to have the most important things here. The electric cooler, got to keep those drinks cool. I did actually for a while have this running off solar power, but I moved it when the sun started getting low in the sky. I moved it off and used a 12 volt, 120 volt, 12 volt converter. So I was running that off a generator that I had for luxuries like fans, creature comforts, things that weren't related to the station but were kind of nice to have. So in addition to all this, I had a 120 volt feed coming in, but it wasn't running any of the station things. It was only running creature comforts, luxuries. A friend had an extra laptop we were playing with, stuff like that. So to fix the problem of the batteries sagging down under load during the night, I had a boost regulator I picked up from Amazon. I didn't bring one of those down to show, but it's a little box about yay big that's cast metal, and it has wires coming out for an input and an output, and it can handle up to 18 amps, and it'll boost from 10 to 13 volts on up to 13.8 volts. And that gave me a regulated power rail. So even if the batteries sag down to 11 volts under the draw at night, I still had a solid 13.8 volt supply for all of my radio gear. So I didn't have any brownout dropout problems. That way I could just connect the radio. I know it's going to get the right power. However, it turns out I needed 2 of these because that radio, the ICOM 7100, can sometimes peak up around 20 or a little over 20 amps if we have to crank the power up. And also to help stabilize the power rail with the high to low current draw swings, I had a 3.5 farad car audio capacitor. I should have brought that down as well, but it's a pretty chunky thing. It's about 1 foot long, maybe 4 inches in diameter, and it has a pretty substantial capacity, and that does a lot to help smooth things out. Also remember, this power rail is running more than just the radio. It's also having to run the power supply for the laptop, the little LED. I had a car turn signal LED that I put wires on to light up the tent in the evening, a nice amber glow so it didn't ruin your night vision too much or keep people awake trying to sleep. But it was enough you could move around, not trip and fall. The Wi-Fi adapter for the access point, my Yaesu VX6R for scanning the NOAA weather, charging my laptop. So all this stuff was running off that regulated rail. So that was another reason I needed to have the 2 boost converters in parallel. Normally you're not supposed to connect power regulators, converters in parallel like this. In theory, you could have one of them is 1/8 of a volt or 1/2 of a volt higher than the other in its calibration, and it'll pass more, and it could overload, and it could this and that. In reality, I tried it before field day. I put meters on both of them, and it looked like it was about a 60-40 split, which put both of them well within their specified ratings. Also, the one that seemed to be running a touch higher voltage, I ran, you can see over here, the one, it's going up to this power rail that feeds everything else. Because I don't know if we're representative of how I wired it. And then it goes back down to the radio. The other one is going straight down to the radio directly. And that helped so that the one that was a little bit higher had to go through a longer amount of wire, more connectors. That's adding a little bit of resistance to help manually balance it closer to a 50-50 split. And maybe I have that. I can't remember. I figured out which one needed to be where and tried to manually balance it while I had meters on it, and it seemed like this was the this configuration was the best that gave me a even balance of how much current was flowing through both of them. And that way I wasn't apt to overload either of the regulators. Ideally, you wouldn't want them in parallel, but it was good enough. It worked for the purposes. So that's all the many things that were in that power setup to run off solar panels, and it was quite a bit of stuff more than I had in mind originally. So here's what the current shunt is. Basically, it's a really high power rating, really low resistance resistor. And it gets put in on the negative wire. The reason for this is when there's a drop across it, because the load is pulling, it's going to pull the voltage on the load side a little bit closer to the positive, because a teeny bit of power is lost in it. So by connecting a voltmeter from the battery ground over to the other side of the shunt, it allows you to measure the voltage across it, and with Ohm's law you can compute. I purchased a shunt that it worked out very nicely. 1 milliamp is, 1 millivolt is 1 amp of current. So if I had 1.5 millivolt reading, I knew that's a 1.5 amp draw. That made the math much simpler than you can buy them, for example, like a 200 amp shunt that has a 50 millivolt drop. But you'd have to do additional math. You couldn't just read it directly off a meter. You'd have to do the conversion and calculation of meter scale to amperage. So that's why I chose a 75 millivolt, 75 amp rating one. I knew it was much greater current than I'd be having. The way these work, you see these little white marks. Basically, it's a plate, and they cut little notches into it so that they get it just exactly to the right resistance. That's actually what it looks like inside of this enclosure. It actually looks like a plate with a couple of cuts into it. And then the wires actually do connect to the sides of the shunt, not to the incoming leads. That way you're really measuring just between the sides of the shunt. You don't have to worry about any minute loss throwing off your reading where the heavy cable is connecting to the terminals on the shunt. So that helps a little bit with the accuracy to get a good reliable reading. Now, to measure, that gives us our measurement on the current. To measure the voltage of the battery, we just connect from that battery side of the shunt. Share the same ground, because the logging meter I have shares the ground with the two channels. So we just put the other meter to the positive and directly read the battery voltage. Now with this, you can see how much power is going in or out of the battery. If your voltage reading on the shunt is negative, you're charging the battery. If the voltage reading on the shunt, if the voltage reading on the shunt is, may have drawn the diagram backward, but I got it so that if the meter read negative, I was drawing power out. If the meter read positive, I was putting power in. Really, all you have to do to change that is you swap around which end is which. So if I plug it in this way, it's going to read positive when it's charging and negative when it's discharging. If I flip it around, now it's going to be reading exactly the opposite, just because you're swapping which side of the shunt gets pulled slightly higher or lower. So here's the screenshots from the software of where I'm reading the shunt. And you can see the difference. This was during the sunny part of the day it looks at. Can I see what the, what does that say? 10 to 12 a.m. it looks like in the top corner of the screenshot. So you can see here it's 12.6 volts and 2.2 amps being drawn out of the battery. Then when we were receiving 13 amps going into the battery and 13 volts on the battery. So we were charging pretty good at that time of day. But that gave, I could pull it up and have real-time readings of what the power was doing going in or out of the battery. So here's the first graph. This is the blue dots are a plot of the amperage in or out. The bottom half of the chart here is all negative current drawing battery down. Top half of the chart that's not shaded is putting power back into the battery from the solar panels. So you can see through the day, we started over here, and the voltage, the green dots are the voltage plot, scatter plot. The line is a average over 60 minutes. And then the same thing, the blue dots are the instantaneous readings for the current. The line is a 60-minute trend average. So you can see, here we started out, the battery voltage was way up there because I had them out in the sun charging for a week or so before the event. The current, we're not losing any. We're not putting a heck of a lot in. Then there hit a point around probably a little after 3 o'clock where the sun got low enough in the sky that we were drawing power down more than we were putting it in generally. The FT8, it's a 50% on, 50% off for equal periods of time. So, we were drawing power in. Then probably around, what would that be? Is that 1600, 1800? Yeah, later in the evening, maybe I repositioned. You can see the spikes where I repositioned the solar panels a little and the average came up. And you can also see the difference between the current here and then the current down here, where receive, it's charging, transmit, it's pulling down. And because of the on or off, and it's drawing more during that time period. Had a question, can you use a shunt for AC current? I'd like to take an AC current measurement. I haven't actually attempted to use that. I don't know if you'd need a different sort of a meter. Really, it's just a big resistor. I suppose it might work. I might be able to get back to that. I might be able to do a sort of a bench test with a low voltage AC transformer and a small load, and that would be interesting to see. Since it's just a resistor, I guess maybe it would work. You'd just have to be measuring the amount of loss across it, but I'm not as familiar with, I haven't had as much experience measuring the AC voltages. I hope that answers the question somewhat. Yeah, so you can see through the day, during the night, obviously it was way down. And then when it comes morning, those solar panels are pushing a lot more current in because the batteries were down. And you can see the voltage start to come back up again. So this graph is of the capacity. Since I had the 1 second intervals of the voltage and the current, I can compute the instant, every roughly 1 second, what the wattage is going in or out, and then I just went with the assumption that it was an average for that 1 second. It's probably not exactly correct, but the cycle is going on or off at, I think it's 15 seconds on, 15 seconds off for FT8. So it's going to be a good enough average. And then I was able to use some formulas and convert that into like watt seconds and then eventually watt hour capacity over time. So over here you can see put a little bit of power into the batteries, because obviously if they're disconnected while I was transporting them, they're going to lose that surface charge a little bit. And before I got the panels hooked up, stuff was running. So it was putting in a teeny bit of charge, and then you can see where the amount of power I was pulling out started to be greater than what was going in. So the watt hours inside of the batteries started going down. And it looks like I pulled probably a little over 1,500 watt hours, 1.5 kilowatt hours out of the batteries at the worst point. And then you can see it leveled off and starts coming up because the sun was up and I was putting power back into the batteries with the solar panels. I didn't quite recover from where I started to where I was. I had to have the batteries out charging once I got home for a period of time, but it didn't do too badly. I think if I did it again, maybe I'd want to try having an additional solar panel and see how that behaves. I am glad I had 3 batteries and not just 2 of them, because 12 volts at 100 amp hours, that's about 1.2 kilowatt hours per battery. And just skimming the comments, looks like that was someone else answering the question that I was unsure of in the comments. I don't think there's any additional questions right now. But yeah, I definitely needed more than the entire capacity of one battery. It's generally bad to run them completely down. It's not healthy for them. I've frequently heard people say you don't want to discharge the storage batteries more than about 50% for their life to be a good long life. So having 3 of them, that gave me a lot more capacity. I didn't come anywhere near that with I used a little more than 1 whole battery worth of capacity. So they were probably about two-thirds capacity charged when, I'm sorry, I'm also distracted. The dogs are running around right now in the next room. About 2/3 capacity was still charged in them at the worst point, and then it started to recover back from that. So that should have been very healthy for the batteries. And that concludes what I was wanting to talk about. I'll leave a few minutes here for anyone else that had questions or wants me to revisit something to get a little more detail. This presentation should remain up on YouTube at this link. So if people want to rewind later and rewatch a portion of it, or share it with someone that they think may be interested, it should remain up. It may take a little while for YouTube to transcode and buffer it and transition it from a live stream to a playback stream, but that should remain up for anyone that wants to watch it later or share it with someone to watch later. Once it goes live, if someone wants to post a question or something, I will try and read the comments and reply to them if anyone has additional questions. I won't be able to do a video reply, but I can at least try and follow up. I see there was a question, were those batteries standard automotive type or deep cycle? So the batteries I got were the Walmart flooded lead acid marine and RV type batteries. It says they are dual use. I think they are rated around 600 to 700 cranking amps, and they're also rated with a discharge rating for deep cycle use, 100 amp hour capacity if you discharge them over 20 hours, which napkin math says that's on the roughly a 5 amp load. So I was pulling a little bit more than that peak, having 3 of them, and my peak pull, we can probably see that. The peak pull, it looks like I was pulling around 26 amps at the absolute worst case. Most of the time it was closer to 25 amps. So I was a little more than what the 20-hour discharge rate to completely drain them would have been. But they're they were the cheapest batteries that I could readily source, which was good because I wasn't planning to purchase them at that point. But yeah, they're supposed to be dual use starting and deep cycle storage, the Walmart RV and Marine batteries. See, were there any other questions as we wrap this up? Hopefully this was a success, and I also look forward to hearing back if people liked the format. I know there was talk of moving to a WebEx format for future meetings, and have to look into, I know the software I'm using is Open Broadcast Studio. It's designed for gamers who are wanting to live stream games to Twitch and YouTube, so I'd have to look and see if it can stream to WebEx. But I'm sure someone will be curious what it looks like behind the scenes and how I did the slides, and I'm standing here, so here's the look behind the scenes, but behind the magic. I've got a green sheet and the camera, and the software sees the green sheet and allows me to overlay the slides on top of the green sheet. It makes it a little more readable. The downside is you can walk across and you can walk right out of the frame. But hopefully that gave you all an interesting topic for a presentation, and thank you for watching. I think I'll wrap this up now. So have a wonderful evening, and hope everyone stays safe and healthy.